When heavy industrial machinery smoothly flattens a thick steel block, you're seeing hydraulics in action. The technology is defined by extreme force and crushing pressure. Because these machines can lift tons of steel or bend metal like plastic, it is intuitive to assume the massive pump at the center is the source of all that force, acting as a high-pressure factory, generating thousands of pounds of energy and pushing it out into the machine. But that assumption is backwards. Hydraulic pumps do not create pressure. Look at this schematic. Take a hydraulic pump, disconnect its output line, and let it freely spit its fluid back into an open tank. It will run all day. If you check the pressure gauge attached to the line, it registers absolute zero. The pump is driving the system, yet the gauge reads zero. If the engine turning the pump isn't the source of that crushing force, we have to look elsewhere in the circuit to find out what is. Every hydraulic system starts in the fluid reservoir. It might seem strange that engineers rely on specialized oil instead of something cheap like water, but water has engineering flaws that make it unsuitable for heavy work. It causes steel components to rust, it boils or freezes at common operating temperatures, and it lacks viscosity. Water is simply too thin to properly lubricate high-strain mechanical parts. We use specially formulated hydraulic oil, typically graded as 32, 46, or 68 based on its thickness. The reservoir stores this oil, but its real job is giving the fluid a quiet place to sit so it can shed excess heat and allow contaminants to settle to the bottom. From that tank, the oil is pulled up by the hydraulic pump, which is driven by an external electric motor or combustion engine. The pump has one primary purpose: to generate continuous fluid flow. This cross-section of a gear pump shows why it is called a positive displacement pump. Its internal geometry is strictly defined, meaning it forces an exact volume of oil into the system with every single rotation. The mechanical tolerances are so tight that they allow practically zero backward slip. As long as the motor spins, fluid is pushed forward into the circuit. But even at high speeds, moving gallons of oil every minute, the pressure gauge stays flat. The pump provides motion. To translate that motion into raw power, the flowing fluid has to crash into an obstacle. Once the oil leaves the pump, a directional control valve routes it into a hydraulic cylinder. Inside that cylinder is a piston, and sitting directly on top of that piston is a massive, unmoving payload. To understand what happens next, you need to know one physical property of hydraulic oil. Under mechanical stress, it is practically incompressible. Even under hundreds of bars of force, it yields by only about 1%. This split-screen schematic shows the moment of conflict. On one side, the relentless positive displacement flow from the pump is forcing oil into the space. On the other side, the heavy load refuses to budge. Because the fluid cannot compress, it has nowhere to go but forward. That physical resistance to the flow, the oil fighting against the weight of the obstacle, is what actually creates the pressure spike in the system. This creates a dangerous scenario. Because the oil cannot compress, pressure builds instantly. If the load is too heavy to move, the pump keeps forcing fluid into a blocked pipe until the system fails or a line bursts. To prevent that, every hydraulic circuit requires a pressure relief valve. It is engineered to monitor the line and pop open just before the breaking point, bleeding the excess highly pressurized oil safely back into the tank. Hydraulic power relies entirely on forcing an unyielding fluid against a heavy wall until moving that wall becomes the path of least resistance. Viewed as a whole, the hydraulic power unit functions as a dynamic, continuous loop, translating rotary motor speed into linear pushing force. Designing this loop requires a mathematical balancing act. This chart breaks down the three distinct pressure metrics that must be aligned to ensure the system is both functional and safe. At the bottom is the working pressure, the actual force required to move the specific load. Just above that is the relief pressure, the safety ceiling set roughly 10% higher to allow for safe operation without unnecessary venting. At the top is the rated pressure, the absolute maximum mechanical stress the physical pump can survive. This must always remain higher than the relief ceiling. If the pump's limit is lower than the safety valve setting, the pump will fail before the safety system can even react. This careful balance is necessary because hydraulics cannot store power. While a pneumatic system can compress air and hold it inside a tank for later, hydraulic systems only generate their force in real time, exactly when the motor is spinning and pushing fluid against a load. The next time you see massive machinery at work, you'll know it isn't the pump flexing its muscles. It is the unstoppable physical reality of a fluid with nowhere else to go.